The internet's physical infrastructure consists of cables, routers and other equipment that carry and relay traffic. But what actually gets transmitted, and how do the signals know where to go? And for that matter, if there's different equipment in different countries made by different companies, how do they all understand each other? How the physical infrastructure is used and interacts is governed by a series of rules called protocols. Protocols are just standardised ways of doing something, and in computer networking, protocols describe the various processes involved in sending a message from one machine to another, covering what gets sent, how to actually transmit it, how to check it got there, and everything in between. You've probably heard of one of these protocols already, Internet Protocol, or IP. Internet Protocol is the Internet's primary navigation system. It's how the traffic from your computer knows where it needs to go, and it's how the routers get it there. The most famous part of IP is arguably its addresses. Every device on the network, which we call a host, has one, and they're how hosts describe where they are and how traffic sent between them knows where to go. IP addresses are sequences of 32 bits, but that's neither particularly readable nor is it easy to remember, so instead of 32 bits, we usually write it as 4 groups of 8 bits, which we call octets. We write those octets in decimal instead of in binary. IP addresses are actually made of 2 parts, which represent the network and the host. To tell them apart, each address comes with a subnet mask that indicates how many bits are in each. You can think of IP addresses as being a bit like house addresses, composed of a street and a house number. And much like house addresses, hosts write IP addresses on the front of anything that they're sending. And what they send are packets, literally packets of data, with a sticker on the front called a header, which lists, among other things, the IP address of the destination and the sender. Packets tend to be very small, tens of bytes on average, and a lot of networks won't let you send much beyond 1,000 so you don't clog the network up. In fact, because they're so small, it's likely that any data you want to send isn't actually sent in one piece, but rather it's broken up into fragments, distributed among lots of small packets and reassembled on the other side. You can think of network communication as being like mailing somebody a puzzle, but one piece at a time. What Internet Protocol actually defines is what IP addresses look like. It also defines what information is in the packet's header and the fragmentation process I described a moment ago. Crucially, it also describes how routers handle packets. Packets traverse networks by routers retransmitting them between each other, one at a time until the packet gets to its destination host. When I said that traffic traverses the internet by jumping between ISP data centres, that's exactly what's happening. They're jumping between core routers in each data centre. But how do routers know where to send packets? Especially on the internet, core routers must be hooked up to lots of other core routers, so there'd be endless routes a packet could take. To work it out, each router has a routing table. This is a list of networks it's aware of, and what it considers the next stop on the best path there. When a new packet arrives, its network identifier will be looked up in the routing table, and it'll be forwarded to the router listed as that network's gateway. In other words, the next stop on the way to it. But where do these routes come from? Routing tables can be pre-programmed, but they're normally created and maintained on the fly. IP doesn't actually specify how to do this. Instead, it leaves it to routing protocols, which suss out the best paths on each network and spread them around, adding in any new routes they found and flagging any which have gone down. Exactly what constitutes the best route depends on what routing protocol you're using. For example, Route Information Protocol uses hop counts, whereas Open Shortest Path First looks at transmission speed. Well, that's the case on normal networks at least. The thing is, on the open internet, neither of those would actually work. It's just too big. And that's a problem, because core routers have to maintain global routing tables, which are maps to every network in the world. Fortunately, there's a special routing protocol for this, Border Gateway Protocol, or BGP, which routes between entire ISP networks, otherwise known as autonomous systems. When lower tier ISPs pay for transit from higher tier ISPs, access to these global routing tables is really what they're buying. BGP is a protocol worth knowing about, not least because it's the internet's unsung hero, but also because if you've ever heard of a government turning off a country's internet, much like Hosni Mubarak did during the 2010 Arab Spring, stopping BGP peering is often how it's done. BGP screw-ups aren't always malicious though, as Turkish ISP TTNet found out when a bad config accidentally made them the #1 destination for all internet traffic in Christmas Eve 2004. So Internet Protocol covers the addresses and routing protocols cover making the tables themselves. There's still quite a lot to do. How do we know what we're sending in the first place? the payload that Internet Protocol might demand we break up? And how can we be sure it got there? And never mind all this abstract stuff, how do we actually transmit it? Network communication isn't handled by a single protocol. Rather, it's made possible by the combined efforts of a team of protocols that work together seamlessly, supported by helpers like the routing protocols. To make sense of what does what, we organise protocols into a network model, where each protocol is said to belong to a layer, which describes what it does and how close it is to the physical hardware. Right at the top is the application layer. This describes the data you're sending, and it's usually tied to a specific use case. For instance, websites use Hypertext Transfer Protocol, and emails use Simple Mail Transfer Protocol and Post Office Protocol. You'll also get helper protocols like Transport Layer Security, which encrypts the payloads from other protocols. You'll have probably seen this before. Every time you visit a website and there's a padlock or HTTPS in front of the URL, this just means HTTP secured with TLS. Along with the routing protocols we mentioned earlier, TLS can be said to sit in the application layer. The helper protocols like these really span multiple layers, if they can be said to fit in the model at all. Below application is the transport layer. At minimum, this describes who the payload is for. Just like houses can have many people living in them, hosts will have many apps running on them, so when a packet arrives at the host, there needs to be a way of working out who it's meant for, and how it does this is a port number. Think of each host as having a mailroom full of pigeonholes, each with an ID. The pigeonholes are the ports, and their IDs the port numbers. When an app loads, it'll ask to be bound to a specific port. In other words, it'll ask for sole use of that port as its in-out tray while it's running. In principle, apps can bind to any port, but protocols do have favourites. HTTP prefers port 80 for instance, and the email protocols prefer 25 and 110 respectively. But whatever the number, once an app is bound, any packet arriving with a header bearing that port number will be sent straight to it. Transport layer protocols also describe, if desired, how to check a payload has actually arrived. But as I say, if desired. The no-frills send and hope approach is User Datagram Protocol, or UDP. It specifies the port number and not an awful lot else. And that's fine for certain circumstances, streaming and playing games for instance. With those you'll put up with a certain amount of buffering from lost packets. But sometimes we do need more of a guarantee. Downloading half a file isn't very useful, and neither is sending a third of an email. So for guaranteed delivery we use Transmission Control Protocol, or TCP. TCP ensures the whole packet gets delivered by splitting the data into segments and having the destination acknowledge it's received each one, in order as they arrive. If any go missing along the way, they're automatically re-requested until the entire payload is delivered. And once complete, the sender formally signals it's finished. Below transport is the internet layer. This is where Internet Protocol, its namesake, lives, and as we've already covered, this defines IP addresses, routing, and other things like fragmentation. IP also, of course, adds the source and destination IP addresses to the packet header. I say the packet header, there isn't actually one packet header per se, but rather each protocol adds its own header after the last with its own information in it, and these are read backwards when the packet gets to the destination host. On those fragments though, IP fragments aren't the same as TCP segments. In fact, IP and TCP aren't actually aware that the other exists. TCP is not aware of what generated the original payload, and neither is it aware of how IP intends to send it, what address it's going to, and whether or not that segment needs to be fragmented. Equally, IP is not aware of whether TCP has segmented the payload, and if it has, which segment it happens to have been handed. On the other side, IP also has no idea how a packet will actually be transmitted. Network protocols are deliberately designed to be agnostic of each other. Doing so means each protocol can focus on one thing, be it sending an email, encrypting an email, or moving the packets containing the email around. The result of this is that the network stack is modular. Protocols can be easily swapped in and out depending on what the situation calls for, and new protocols can be easily integrated. Finally, below the internet layer is the link layer. This describes how network equipment actually transmits the packets, and you've likely heard of two of its protocols already, Ethernet and Wi-Fi. These describe how to transmit over short distances using copper wires and radio waves, which are pretty handy for local networks like the one in your home. Specifically, they implement parts of the IEEE 802 standard, which is what actually does the describing, whereas Ethernet and Wi-Fi provide a way to do it in practice. Link layer protocols don't use IP addresses. A packet's destination IP is its final destination, the host it's going to eventually, and the IP address looked up in the routing table is the host it's going to next. The trouble is, neither actually tell you how to get to that host. And this is what link layer protocols care about. Not which host, but rather which network interface. Literally the Ethernet port, Wi-Fi antennae or otherwise that's directly connected to the next host. You identify a network interface by a Media Access Control Address, or MAC address. This is just the serial code of the port of antennae given by the manufacturer. But this means they're unique and they don't change, which is handy when ensuring a signal gets from one specific place to another. So before passing a packet to the link layer, the IP address of the next host has to be swapped out for the MAC address of the network adapter connecting to it. What handles this translation is another helper protocol, a common one being Address Resolution Protocol. So the link layer and internet layer are still unaware of each other, and the transition is seamless. Strictly speaking, we're also not dealing with packets at this level. Link layer protocols do add their own header, but they also add a footer, so it's more accurate to say that the link layer wraps the packet into a new package that we call a frame. And while packets are routed across a network, frames are switched from one interface to another. This model is called the TCP/IP model. I've explained using this because it's quite simple, but in practice there's another model that's more frequently used, the Open Systems Interconnection model, or the OSI. TCP/IP and OSI are roughly analogous, with the main difference being that OSI has 7 layers instead of 4, splitting up the application and link layers into finer grained detail. Because of this, not all protocols fit neatly into it, and some can be said to span multiple layers, if not changing their layer completely. You may sometimes hear of protocols, networks or equipment being referred to by their layer. This usually means the OSI model, and like the layers themselves, it's just a shorthand way of describing how low level something is. And when I say low level, what I'm talking about is how far removed a protocol's implementation is from literally just being a circuit on a chip. Application layers are, unsurprisingly, handled by an application, say your web browser or some other app you're running. Pretty abstract. The transport and network layers are handled by your operating system. The link layer by the network interface's driver in tandem with its firmware. And the physical layer is the interface's hardware itself. This is where it is a circuit on a chip, and is as low level as you can get. As a final point, who creates and maintains protocols? Much as with the internet itself, it's a combination of international non-profits and private companies. Most of the protocols we've encountered so far were created and are maintained by bodies now supported by what's called the Internet Society, a non-profit founded to advance the internet's open development, building on previous work by the US government. In particular, TCP/IP, TLS, HTTP and many other standard protocols are the work of the Internet Engineering Task Force and the Internet Research Task Force. The former also being responsible for popularising the Request for Comments or RFC style of open peer review that's used to publish and refine these protocols, as well as the TCP/IP network model we saw earlier. Another major body is the Institute of Electrical and Electronics Engineers. This is a professional association that, among other things, maintains the 802 specification we saw earlier, which is itself what Ethernet, Wi-Fi and Bluetooth derive from. The latter two of these in fact have their own non-profits which maintain them, those being the Wi-Fi Alliance and the Bluetooth Special Interest Group. The final major player is the International Telecommunications Union. This is a body of the United Nations that's responsible for promoting telecommunications standards. Among other things, they also maintain standards for fibre optic transmission, and indeed the 3G, 4G and 5G cellular network standards your smartphone uses. The IEEE, IETF and ITU are all independent organisations that do sometimes publish clashing standards, but they also frequently collaborate. Their other major collaboration partners are the private sector. Often commercial tech companies focus on proprietary contributions, like Cisco's IGRP and eIGRP routing protocols which have widespread use. But in addition to their own projects, they often help fund the non-profits I mentioned earlier, and often allocate their own staff to work on standards and projects with them. In summary, the operation of the Internet's infrastructure is governed by protocols, which describe a standardised way for equipment to communicate. Protocols are created and maintained, much like the Internet itself, by a combination of non-profits and private companies who work to create global standards that mean wherever something is made and whoever buy, it has standardised protocols with which it can be confident it can communicate. Protocols are specific in purpose and address a single aspect of communication, like network addressing. They also operate independently, allowing them to be swapped in and out to optimise for a given situation, and for new ones to be easily integrated. Unsurprisingly, there's quite a few protocols about. So to make sense of them all, we organise them into network models, where we say each protocol belongs to a layer that roughly describes what it's responsible for and how low level its operations are. The lowest, like Ethernet and Wi-Fi, handle the raw transmission itself. Middle protocols like IP describe how traffic navigates its way around the network, where it's going and what route it'll take there, or TCP, which checks it's arrived and once it has, says which app it's for. And finally at the top of the stack is what's being sent in the first place. Routing works by packets hopping between routers one at a time, initially guided by MAC addresses, then heading for the network specified by their IP address, and when they get there the host specified by their IP address, and when they get to that host, the port number specified by their transport protocol. Everything the packet needs for its trip, or rather the frame when it's wrapped up, is found in its various headers, each containing information contributed by a different protocol to help get it to the destination host and to the destination app when it gets there. All these protocols come together to make up a packet. Some span multiple layers and others aren't easily placed. But that's okay. Network models are supposed to be guidelines to help you understand, they're not rigid classifications. The point is that collectively, all these protocols work together to create a packet and get it from one side of the network to the other. And mad as it sounds, whether that network is in your home or part of the wider internet, the protocols involved are largely the same. Truly, there's a protocol for everything. There's even one called RSVP, which sadly doesn't let you respond to wedding invitations. Which is a real shame, because if it made use of HTTP error codes, some of the choices would be perfect.